It gives me great pleasure to dedicate my contribution to the special issue of the Journal of Object Technology to my good friend and colleague Martin Gogolla upon that very special occasion of his officially becoming a senior citizen. Actually, I guess I should have said formally becoming a senior citizen, since I know that Martin is very much fond of formal methods. And speaking of formal methods, much of this article has to do with their use in the design of component-based software. Specifically in this paper, which is titled Forgotten Interfaces, a critique of component-based models of computing and a remedy, I argue that while formal methods can and often do play a crucial role in the design of component-based software, they are not sufficient. Moreover, I claim that they are not only insufficient, but unless their shortcomings are fully understood, they can be dangerous. Dangerous because they may foster a false sense of security about designs that are inherently inadequate, but may seem quite correct, and which analysis might actually prove seem to be correct. So the primary reason that the component model has proved to be attractive to computer science theoreticians working on formal methods is its highly modular, that is, black box nature, which promises a relatively simple and incremental approach to software analysis. That is, no matter how complex a component is internally, it can always be reduced to a conceptually simple input to output box or converter based on what can and cannot pass through its interfaces. This is a perfectly reasonable approach as long as all the interfaces of a component are fully accounted for, and this is an important condition. See, I claim that missing important interfaces is a common failing of practically all the theoretical component models I've seen so far. So the interfaces that I'm talking about are the implicit and sometimes explicit interfaces that a component implementation has, the interfaces it has to its supporting layers, or as they are referred to in the paper, its platform. More specifically, the implementations of all component models rely on the services, for example, the API calls, and resources provided by the underlying component framework. A component framework is, of course, responsible for realizing the desired semantics of its component model. This includes things such as methods of intercomponent communications, models of concurrency, models of computation, and the like. In turn, such component frameworks typically themselves rely on other software layers, such as an operating system, for example, and so on, all the way down to the hardware itself. Together, these supporting layers constitute what I call the platform for a component-based application. So the key argument put forth in the paper is that the qualitative and quantitative behavioral characteristics of the platform cannot always be idealized or abstracted away because they can have a fundamental impact on the actual runtime behavior of components, as opposed to its specified logical behavior. So a platform is ultimately rooted in hardware, which makes it a physical device. This means that it has finite communications, finite memory, and finite computational capacities. In reality, no computation or message exchange takes zero time. Because it is inherently physical, a platform is inherently imperfect and even failure-prone. Moreover, particularly in case of cyber-physical systems, it interacts with a highly concurrent, asynchronous, and generally unpredictable physical environment. Good engineering practice instructs us that when designing software, or any system for that matter, it would be highly unprofessional and irresponsible to ignore the impact of such imminent properties of platforms that the platform can have on the design. For example, a physically distributed component-based application that ignores the possibility that there may be long and unpredictable communication delays between peer components that are situated on different physical sites, it will not be able to react correctly to such events. So as a possible way out, the latter part of the paper proposes a methodology that can help to deal with this state of affairs, something I call the acceptable platform design pattern. The paper also includes an appendix that provides an explanation of, but not an excuse for, why this critical problem has been ignored for so long. In summary, the core message of the paper is that when designing modern software, we must treat it more than just a problem of applied mathematical logic, but as a fully fledged and potentially messy engineering problem. Finally, in conclusion, I take this opportunity to congratulate my colleague Martin on his work to date and yet to wish him yet more successes in his future work, to which I look forward with anticipation, even if he is a senior citizen. Thank you, Martin.